Find the Maclaurin series for f of x equals natural log of the quantity 1 plus 3x. Assume that f of x has a power series expansion and that the remainder Rn of x approaches 0. Then determine the radius of convergence. The Maclaurin series is the Taylor series centered at x equals 0, and the formula is shown below. We'll find the first several terms of the Maclaurin polynomial, which hopefully we can then use to determine the pattern to write the formula for the Maclaurin series. Let's begin by determining the first three derivatives of the given function f of x equals natural log of the quantity 1 plus 3x. F prime of x equals 1 divided by the quantity 1 plus 3x times the derivative of 1 plus 3x, which is 3. F prime of x equals 3 divided by the quantity 1 plus 3x, which to find the second derivative, we need to write as 3 times the quantity 1 plus 3x to the power of negative 1. The second derivative is equal to negative 3 times the quantity 1 plus 3x to the power of negative 2 times 3, which simplifies to negative 9 divided by the square of 1 plus 3x, which to find the derivative we should think of as negative 9 times the quantity 1 plus 3x to the power of negative 2. The third derivative is equal to positive 18 times the quantity 1 plus 3x to the power of negative 3 times 3, which simplifies to 54 divided by the cube of 1 plus 3x. And now because the Maclaurin series is centered at x equals 0, we need to evaluate all these functions at x equals 0. F of 0 equals natural log of 1, which is 0. F prime of 0 is 3 divided by 1, or 3. F double prime of 0 is negative 9 divided by 1, or negative 9. F triple prime of 0 equals 54 divided by 1, or 54. Here are the first four terms of the Maclaurin polynomial. And now we substitute in the function values we just found. Notice the first term is 0. And now let's simplify if we can. 9 divided by 2 factorial is just 9 halves. 3 factorial equals 6. 54 divided by 6 is equal to 9, giving us plus 9x cubed. Because this second term is a fraction, though, it's going to be helpful to have all the terms as fractions. Let's write 3 as 3 divided by 1. Keep the pattern going. Let's write 9 with the denominator of 3 as 27/3. And now see if we can recognize the pattern to write the formula for the Maclaurin series. If we let n start at 1, notice the denominator would just be n. The powers on x would also be n. And the numerators are powers of 3, which can be expressed as 3 to the power of n. The only thing left to deal with is the alternating sign of positive, negative, and so on, which we can take care of using negative 1 to the power of n plus 1. The Maclaurin series is the sum from n equals 1 to infinity of negative 1 to the power of n plus 1 times 3 to the n times x to the n, all divided by n. Now, if we did want to start at n equals 0, we can also write the Maclaurin series as the sum from n equals 0 to infinity of negative 1 to the power of n times 3 to the power of n plus 1 times x to the power of n plus 1, all divided by n plus 1. Let's go ahead and use the first series and now determine the radius of convergence. We'll do this using the ratio test on the next slide. Recall for the ratio test, we determined the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n, which must be less than 1 for the series to converge. A sub n is the given formula, and I've already determined a sub n plus 1. Let's set up the limit. Again, the limit is the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. And now let's write this quotient as a product by multiplying by the reciprocal of a sub n. And now let's begin to simplify. Because of the absolute value, the negative 1's don't really matter, but notice negative 1 to the power of n plus 2 divided by negative 1 to the power of n plus 1 simplifies to 1 factor of negative 1 in the numerator. 3 to the power of n plus 1 divided by 3 to the n simplifies to 1 factor of 3 in the numerator. And x to the power of n plus 1 divided by x to the power of n simplifies to 1 factor of x in the numerator. We can now write the limit as n approaches infinity of the absolute value of negative 3x times n divided by the quantity n plus 1. As n approaches infinity, n divided by n plus 1 approaches 1, and therefore the limit equals the absolute value of 3x, or 3 times the absolute value of x, which we know must be less than 1 for convergence. Solving for the absolute value of x, we divide both sides by 1/3. The absolute value of x must be less than 1/3, which indicates the radius of convergence is 1/3. We also know the series converges on the open interval from -1/3 to +1/3, but if we wanted to find the interval of convergence, we would have to test the endpoints for convergence or divergence. Before we go, let's take a look at the graph of the original function, as well as the first 3 terms of the Maclauring polynomial. In red, we have the graph of the given natural log function. I've also plotted a point when x equals 0, which is at the origin. And now to graph the degree 3 Maclauring polynomial, and we can see it's a good approximation for the given function around the point 0, 0. I hope you found this helpful.